All right, so still in chapter 8. We did a couple of problems on shear stress analysis, shear caused by bending. And we're going to do some additional problems. These two are nice because we need to go over the steps on evaluating, actually drawing the diagrams, and we need to size for bending the beam, and then evaluate it for shear. Okay, so it says specify suitable wide flange. This is inch series wide flange beam made from ASTM A992 structural steel to carry the load in the figure. And then companion problem. By the way, I forgot to bring my textbook with me, so I need to use the PDF, which it's missing annotations, and I need to download it. Wow. Let's see. So download this or copy image and go to Paint. All right. So here we are. Select all, crop, and we're even given, so they are assumed building like structure. You can see to the right was part of the problem statement to use the equations sizing for building like structures. And I said I need the textbook, so PDF. All right. So I'm in Paint, and to size it for bending stress, okay, we need to, of course, draw the shear force bending moment diagram. Before that, we need to find the loads, the supports. So, okay, let me make some notations. And I also want to lower it just slightly. Select all. Make some notation. I have this point A. This distributed load has the equivalent concentrated load at 10 feet that is in the middle. So it will be just for that I'm going to introduce a notation. So this is what F equivalent for the distributed load. So I have A, and then there's point B. I have C here, there's D, and then there's E. Okay, so we need to evaluate RA and RD. What is the equivalent load to the distributed load? You just multiply. It's in general is the area. Here would just be a matter of multiplying. I'm hiding the text actually, so and this is just equivalent. So it's 4 kilo-pound-foot times, and then 8 plus 8, it's 16 plus 4, 20. So it will be 20 times 4, and that's 80,000 pounds, or 80K. 80K. Let's work in K. All right. So to get the reaction at the supports of some moments, if we sum it about A, result we get a reaction at D. Okay. So I said some moments about A, and this distance we said is equal as the middle. So this one here is 820 divided by 2, that's 10 feet. Okay, so we have negative 15 times 8, negative 80 times 10, and then positive RD times 16 and then negative 12 times negative 12 times 20 equals 0. Okay, so this, or we get from here RD at, so we have a 15 times 8 plus 80 times 10 minus 12 times 20 over 16. That's 42.5. Okay. We'll see if we've got it wrong when we verify summing forces in the y direction. Some moments about point D now have equilibrium. So there will be negative RA, our unknown, times distance 16 plus 15 times, what's the arm of 15? K, it's 8. Okay, so positive, or rather negative positive, positive again, there will be 80 times this distance. So I have 8 plus x 16 minus 10, that's 6. And then I have another negative moment caused by the 12K, arm is 4 equals 0. All right, so RA, that's 15 times 8 plus 80 times 6 minus 12 times 4. And this is 552, and then divided by 16, that's 34.5. So RA, it's a positive 34.5 K, and it's expected. Both of them should be positive to resist only downward loading. All right, so verification, sum of forces in the vertical direction equals 0. Is it indeed? So I said RA 34.5 K. And this one is 42.5. Okay, so we have 34.5, negative 15, negative 80, plus 42.5, minus 12, and it's not equal to 0. So what have we missed? I expressed doubt about the first one, so let's see again. So it will be 15 times 8, 15 times 8 plus 80 times 10 plus 12 times 20 equals over 1/6. This is 72.5, and I think this fixes the problem. 72.5, because I was short of 30K. So, I'm sorry, this is RD. So 72.5K, the other one stays the same, 34.5. Okay, so again, 72.5 plus 34.5, negative 15, negative 80, negative 12, and this is 0. So yeah, found a mistake, fix it. It verifies. Now I can invest into drawing the shear force and bending moment diagram. So things will happen at point C is no longer relevant to us. Was introduced just to evaluate the loads. We have V, units of kilopounds, and we begin by a 34.5 jump up. So jumping is up, drop is down, so 34.5. And then there's 4K per foot. Again, distributed force above, it's negative. So, and things happen at point B. So let's see, I have the 34.5. 34.5. And then from this, I'm subtracting the area under the W curve. We call this lowercase w curve up to point B. So there will be 8 times 4. So negative, again, 34.5 minus 4 times 8. And this is 2.5. So I'm not yet crossing the horizontal. Horizontal is this. So I need to connect with a straight line. And this is slope is W. And then I have a drop by 15. So positive 2.5 minus 15, then drop that makes it negative 12.5. So I have negative, this whole thing is 15. It went to negative 12.5. And it continues on the same slope. So it was a jump because of this. Slope remains the same. So I'm extending this. So let's see where we're at D. So we're having negative 12.5, to which I'm adding again or another 8 times 4. So negative 8 times 4, it goes to negative 44.5. So this is negative 44.5. Okay, again, this is the axis. And then I have a jump by 72.5. So negative 44.5 plus 72.5, it's 28. So it went to, again, this was 2.5 something. So 28, like right here, this is 28. And then I continue on the same slope, and I need to close it to 0. So diagram needs to close to 0. These are parallel lines. This and this, they should have the same, or they have the same slope. So slope W, slope W, slope W. Okay. So let's see. Is indeed, if I take 28 positive and subtract 4 times 4. No, I'm sorry. I take it back. I forgot about this one. So yeah, I forced it a little bit. It was not correct what I was saying. So I have 28, subtract 4 times 4, so negative 16. And that goes to 12. And then with this one, so let me take it back. Again, the same slope goes to 12. And this is 12. And then if I move a fraction of an inch to the right of E, I close the diagram to 0. Was it clear? Okay, so yeah, now I'm correct. This is positive, this is negative, this is positive. All right, so yeah, I used, maybe it was different color would have been. So this is the actual diagram. The others were just lines. Again, could have used color. All right, so now I'm good. I'm seeing the diagram, V diagram, crossing the x-axis in 2 places. I'll have 2 extreme on the moment diagram. I cannot tell for sure if this is a smiling beam throughout, or maybe there's frowning from between D and E. We'll see. So I have M in units of kilo, pound, foot. I draw the x-axis. Again, we'll have some alignment of points at A, B, D, and E. So draw the x-axis first. And because I have these line, not constant V, but rather sloped, then the moment diagram will be parabolic. And it begins at 0, should end at 0. I don't have concentrated moments or reaction moments at the ends. So begins with a larger positive slope, the parabola, and goes to a lesser slope, and then switches to negative slope. So I'll have a minimum that's a cusp. It's not a smooth minimum because of this jump, rather maximum. So again, it goes like a bigger slope to a smaller slope, but not zero. So again, here the slope is 34.5, like at E. I drew the tangent. And at right before B, the slope was, I draw the tangent to the left of point B, the slope is 2.5 kilopounds. And then I go right of point B, and I see parabola, yes, but it begins with a negative slope, 12.5, and it increases to 44.5. I don't know if it crosses, it looks like it's crossing, has to cross the x-axis in between points B and C. So let's see what the moment is at, net moment, bending moment at D. So I have to calculate this amount of moment. So that's going to be the area of a trapezoid between A and B under the V diagram. I wish more students were in class, because in the second test, really there was no fully correct bending moment diagram. The shear were fine on some of the students, but the bending moment diagram was not fully correct on anybody's paper. Okay, so what's the area of the trapezoid? That will give us the moment here. So it's going to be 34.5 plus 2.5. 34.5 plus 2.5 equals times 8 over 2. Okay, so it's 148. 148, it's the moment at B. To get the moment at D, I need to this positive value, I need to add the negative area of the second trapezoid. There are 3 trapezoids. So I said negative, let me put this in the memory and start fresh. So it'll be 12.5 plus 44.5 times that distance is 8 equal over 2 equals, this is a negative value, plus what was earlier 148 gets us negative 572. Okay, so it goes from 148 to quite a bit of negative. Okay, so it went this way. All right, starting with a slope of 12.5 here, going all the way to 44.5 slope. Okay, if I draw the tangent, so slope is negative 12.5. In this one here, again, I drew the tangent to the moment diagram left of point D. So slope is going to be negative 44.5. Okay. And then my diagram needs to close to 0, moment diagram. And it's a parabola again. So it starts with a positive slope of 28, which goes to negative slope of 12. So something like this. All right, positive moment, negative moment, maximum here was evaluated at 572. So this is negative 572 kilopound foot. If we want to find where the moment diagram intersects the axis, that is, what is this distance here? Okay, let's call it x, m equals 0. We can just set up, so to find m, this is not part of the problem. We might be interested in this. So find x where m equals 0. So we're going to say 148, and then we're going to call this distance A. All right, 148, which A translates here. So is going to be negative. Well, I need to evaluate the moment or the shear at distance A, and that will be a parametric value. So how do I get shear at A? So we'll have this piece. The area of the trapezoid is going to be 12.5. I take the magnitude times this V at, well, I could say X M equals 0 times A over 2. All right. So how do I get this V? Too big of a notation. I'll just say V star times A equals 2. All right. So how do I get V star? I could use similar triangles or similarity. So let's see. Well, with triangles, I said we can use linear relationships. It's probably this stage is more convenient. So let's state linear relationship between V at the 3 points. So there will be what? So I call this point 1. I call this point 2. And this is a point in between where A is like the generic, what we need to find. So we have that is working with x that is A minus so the equation is x minus x1 over x2 minus x1. So I say A minus x1 is 8. And looks like I'm working with, so I need to use xm0. This is not choreographed, but I feel like we should practice a little bit. M equals 0, x minus x1 over x2 minus x1. So that will be a plus a 16 minus 8 equals, and now we're looking at the y, which is v. So it's going to be negative, or rather v star that I called. So this goes y minus y1 over y2 minus y1. Okay, so v star minus v1, that will be negative 12.5. So it's negative positive 12.5 over, and we have negative 44.5 minus this plus 12.5. Okay, so I have what? Two unknowns, this guy and this guy. So in order to get the so I need a second equation, and the second equation is this which this is the second equation, equals 0. Okay. What does that mean? It means that the area of this trapezoid and the area of this trapezoid delimited with V star and A, or xm0 at 0. So this is the second equation. And what is A? Now A is going to be xm, that's when moment is 0, minus 8. Okay, so I can say, I can move the 2 in line with this one, so it'll be 296 minus 12.5 plus V star times xm equals 0 minus 8 equals 0. So I have two equations, two unknown. Again, I wrote the linear relationship between these, and from here on it's algebra. Again, we don't have a need for it in this problem. I'm interested in actually the peak values, and this is the bigger one. So that's the one that we're going to use to in selecting the I-beam. So it says in bending is 0.66 SY. So I'm going to erase this with just a a little bit of an exercise if we want to find where the moment goes to 0. That's useful when we do the full package, slope and deflection. When the derivative goes to 0, so at this point the slope is 0. So this is where the smile, am I saying the right thing? Anyway, so yeah, it's where the slope goes to 0. So we need to calculate design stress that is due to bending. So I have M will be M max, which is this one, M max, divided by the section modular. We're not doing twisting. And this is going to be, the design stress is going to be 0.66 of SY. And we need to find SY for ASTM A992, SY is going to be, well, listed at the back of the book. So we need to go to the appendix and find where it says structural steels. Okay, so ours is what was it? I went over. Actually, I wrote it here. So 992. So 992, it's the last on the list. And we're interested in yield strength. So yield strength is 50 KSI. 50 KSI, okay? This assumes static loading. So 50 KSI right here. 50 KSI. You saw from where we got it. So we can populate this equation. Again, this is 50 times 10 to the power 3 psi, and the moment is 572 times 10 to make it pounds times 12 to make it inches. So work in inches and pounds. And this allows us to calculate a minimum required area moment of inertia. So what is this? Again, the equation holds true seldomly for an available wide flange. So we need to find the minimum value and then find one that is next big or suitable at least, if not bigger, the calculated S mean requirement. So what is S mean required? Is going to be 572, the maximum bending stress, all those negatives. So 572 exponent 3 times 12 equals over 0.66 over 50 exponent 3 equals. So this is 208 inches of power would be 3. Again, this is section modulus. So we need to go to the back of the book and look on where wide flange beams are listed and pick one that has at least 208 section modulus. So we're looking at I-shaped channels, I-shapes. You need to rotate view. Okay, so this one is C channel. All right, and we look at W, the wide flanges, and we are on column. We're using the I-beam as it's meant to be used. Well, I cannot see that fabulous because of what's in the background. We're drawn on the board. So which one has at least 208? 208. So I'm looking at the top value. So I see 267. This is a W27 by 102. So 100 pounds per foot. It's pretty heavy. So yeah, this might be our solution. Anything else on the next page? I think it switches to metric. American Standard Steel. This is not the wide flange, so you need to stay with the wide flange as problem requires. So yeah, we can go with use W27102. So use, again, I'm showing, found an SX. So X because it's the beam is used as it should with flanges up and the web vertical. So W27 times 102. Okay, this is the solution to the bending stress analysis problem. Now we need to evaluate the shear stress. Okay, so we need to go to, let's see, come on, Alt print screen, and we need to add to our problem this information. So select rectangle, and we go with entry D, and we move this up. Come on. We move this up and delete. We need a little bit more. So we, yeah, let me get this also. So copy, undo, 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 undo. How many levels of undo can take? Paste. Let's see, select transparent. All right. So we have it here added to the information for this problem. In order to verify how many or how big the shear stress is, we need to find where the maximum shear is to begin with. So we have the maximum shear is immediately before or immediately left of point D. This is the maximum amount of shear. This is also significant shear, but this one is the biggest. So V max, so now going to tau max due to W, or rather V. So it happens is at point D, where V is 44.5. 44.5 times 10 to power 3 pounds. Okay. This is a wide flange section, and we're going to use the available formula. So stress due to shearing stress in beams. Rotate, rotate, rotate. And remember, for I-beams, we have an approximate formula. So let's find that. Where is it? Okay, here it is. So distribution of shear stress and thin web shape is our case. I could erase this. I could erase this unless you want to take a picture before I do. So take your photograph because I'm going to erase this so that we can see better. So we decided what to use. It's this one. And 1, 2, 3, take your pictures. Be popular with friends as you do. Put these on any like Instagram or the new Twitter. I'm sorry? You send it to the entire group. Yeah, that's solidarity. Group solidarity. Okay, so we look at this equation. It says tau max. It's tau max is going to be approximately, so referring to this, is going to be V over T times H. Okay? So what is T? Is the web thickness, and H, as you can see, H is measured as the depth of the flange, or the I-beam. Sometimes this is just this one. So yeah, we're going to apply directly this equation. So we have V, what was it, 444, what are the 44.5 times 10 to the power 3. And then below I have, I can go to the paint and get the thickness. So it says web thickness, 515. And then H was the depth. Okay, so depth is 27.1. 27.1. All right, so let's see how big this is. Again, it's an approximation. So 44.5 exponent 3 over 0.515 over 27.1 equals, this is 3,188.5 psi. Okay, and this is going to be the design stress. All right, so let's verify the design factor. So I'm saying that what equals tau d, and I said that tau d is yield strength in tension divided by what was it? I mean, yeah, like we can just evaluate the what is 0.4 times that's y, compare with the design stress. So, or we can just say it's 0.5 yield strength in tension. This is approximation of yield strength in shear over the design factor. Okay, so based on this equation, the design factor was going to be 0.4. Take the inverse, divide by 2. That's 1.25. Is it clear? You can go to that one page where all equations for sizing, including structures, is. So we evaluate n, and we need to, make sure that is greater or equal that than 1.25 question mark. All right. So I have it. Sy was 50 ksi. So again, this is 3188.5. This is 50 times 10 to the power 3. Okay, so what is n? N is going to be 0.5 times 50 exponent 3 over 3188.5 equals, and appears to be 7.84, which is way bigger than 1.25. So as expected, shear is not an issue most cases. It happens to be an issue when beams are short, close to supports, where we don't have, in general. So short beams close to supports where shear is large and bending is less. So was it clear what I did? Okay. Please watch, those of you who came or not in class, watch the videos, because it was a little bit of a useful conversation on drawing shear and particularly bending moment diagram when we have distributed load with concentrated forces. In test number 2, I was saying earlier, it's on the recording. I haven't seen a clear, correct, fully correct bending moment diagram for problem 1. It was stated in such that if you can do some mistakes but still extract from the diagram the maximum bending moment. All right, let's look at let's see how much we can undo of this. Okay, all right, all right, all right. So the second problem, this is for a metric case. So select all. I need to clean the board. I forgot to ask you to take a picture. Do you want me to blank the screen? So last, it will be just for this one. Or you took notes. All right, so back to PC. Where? This one? This one here. Well, we need to go in the text. So in the appendix, when properties of steels end, design stress guidelines. So we're at appendix 17, and yes, I'm just curious on to it. I'm seeing it for aluminum. Was it aluminum? It was not aluminum. Yes, sir. I believe it was. This was not aluminum. Our problem was not in aluminum. Yeah, this was for steel. This was for steel. Oh, so you're telling me I used the right? Let's see, mate. You might be. I'm verifying myself. Okay, we're verifying yourself. So ours was structural steel, and this is design stress for bending, for shear. So for direct shear and for torsion shear stresses, this is the equation. So I made use of this equation. Oh, I'm not projecting. Come on, projector. All right, so design shear stress, direct shear, and for torsion. So ours will be of the direct shear type. We evaluated the design shear stress, and then I used this equation. All right, so what was it? Or rather this one, 0.5 SY over N, and evaluated N. And here for static loaded, well, it says manner of loading 0.2. But again, the problems, this group of problems had recommendation to go with essentially 1 over 2N to be equal to 0.4, I believe it was stated for this problem. I can go back to the paint. No, it was 4.4 and 0.44. Yeah, what's this? Okay. Let's go to the second problem of this type, but it's for a metric I-beam and for a also material that is specified, and we need to draw or evaluate the loads, draw the shear force Bay moment diagrams, and select the section, and then an I-beam that is, and then verify for where maximum shear is due to bending occurs. What is the design factor? Okay. So let's see. We have a simply supported beam with overhangs. I have point A. This is 22. But it says European. So we need to work in, everything in pound, inch, and then convert the maximum shear value found and the maximum bending moment found into millimeter, and work, again, it's European shape, that's metric. So I have point A, this is point C, point D. I kept B for the middle of this. So what was it? So middle, this is F equivalent of W, this is W. And it's going to be 80 times 22. 18 plus 4 is 22, so 22 times 80 equals, that's 1760 pounds. Okay. And with this, we can Now evaluate reactions at A, reaction at C. Okay, so we sum moment about point A to its equilibrium to get RC.
I hate to interrupt you, but I think that's figure 843.
I'm using the wrong figure. Well, I started the program. I'm going to finish it this way. Was part of what I cropped from the text. Probably in let's see, shearing stress. So probably was what was millimeters. So what problem was that? What problem I'm solving?
Text is from 842.
Yeah.
And the figures for 843.
So I use this figure, but we need to use this one.
The one to the left. The one right on top of it.
This one.
Yeah.
Okay, no problem. I mean, it looks a little bit with the overhang and partial. Okay, yeah. Let's switch to this one. There is a useful difference. So let's say all print screen. I'm gonna go here and paste, and so crop this one. You said this one I should use, yes? Copy, undo, and paste. And I haven't invested too much time into this one. Yeah, it surprised me that we have. I mean, it was not first time we have loads in pounds and area or beam properties in metric. So yeah, I have point A, it's point B, and then C would be, this is 4 plus 2, that's 6. So half distance over where W happens, and move this up where I know I'm not obstructed. So this is F equivalent. And what is 6 times 50? 6 times 50. 300 kilonewtons. And then, so this would be C, and this is D and E. And I need to find RB, and I need to find RE. Summing moments actually will be about point B now. And what do we write? We write positive 15 multiplied by 2.5, and then negative 300 times the arm is going to be 3 meters. And then I have another negative moment. It will be 20 K times 4. And then positive moment of RE. So RE, and the arm of the force is 6. Okay, equals 0. So this will give us RE. Okay. So let's assume this goes to the side, change sign. I'm just working with this, and then change negative to positive. So 15 times 2.5, negative 300 times 3, negative 20 times 4 equals over 6 equals, I have 157.08, 157, I'll say 0.1 kilonewtons. Let me put it here. So 157.1 kilonewtons. And then I'm summing moments about point E. Okay, so I have a positive moment, 15 times the full length of the beam. That's 6 plus 2.5, that's 8.5. Okay, so fulcrum. And then I have a negative moment, RB times the arm, and that's 6. And then I have so negative positive moment would be 300 kilonewtons times this distance is 3. And then I have another positive moment, that's 20 times 2 equals 0. So RB now is 15 times 8.5 plus 300 times 3 plus 20 times 2 equals over 6 equals, I have 177.9 kilonewtons. All loads point down, reaction forces should be up, at least from that perspective we're correct. So let's verify. Sum of force in the vertical direction is indeed 0. So I could actually write it as negative 15, positive 177.9, negative 300, negative 20, positive 157.1. Is this 0 or very close to 0? Okay, so negative 15 plus 177.9, negative 300, negative 20 plus 157.1, and this is indeed 0, so we're correct. Everybody follows? Okay, so let's draw now the V diagram. Units are kilonewtons, and I'm using this seam between the two boards as the x-axis. So I need to align the diagram with some singularities, things that happen on the beam. Okay, so 15 kilonewtons is down, so there's a negative so diagram starts with negative 15, and then I go horizontal, nothing changes, and from 15, which is a little bit big on the diagram given the values that I'm encountering later. So I have set 15 negative plus 177.9, 177.9 equals. That's 162.9 positive. So this was negative. The jump was to 162.9 by the amount 177.9. Okay. And then I have a linear drop, with a slope of 50 kilonewtons per meter of the shear. And let's see what the value, here I have another drop, a sudden drop at D. So let's see what the value right before point D is. C is no longer of concern to us, was a point that we had a need when calculating reactions. So this is a fading C, like a Roman mosaic. All right, so I start here and I go linear. So 162.9 that I have, I'm subtract, it's a positive value, I'm adding a negative value, which is the area under the W curve up to point D. So it'll be 162.9 negative 50 times 4 equals. So this went negative to negative 37.1. Negative 37.1. So negative 37.1. And again, a line, and the slope is 50 kilonewton per meter. Here's where I have a drop by 20. So another drop, or a drop because of this concentrated force. So I went to, so negative 20 is negative 57.1. Okay, and continue on the same slope. And then I close the diagram to 0. So let's see, negative 57.1, this value here, plus the leftover area, so, or rather negative, further negative, 2 times 50 equals 157.1 with negative in front. Immediately right of point E, the diagram goes to 0 due to the reaction at T, and then nothing happens. It's like the free beam, no load. Was it clear? Okay. So I think we have a correct V diagram. This is positive. This is negative. This time is directly useful. Earlier we evaluated where moment goes to 0, but here we need to know where moment goes to maximum, because when shear goes to 0, I mean, we'll have a inflection point with a maximum or minimum here, and then we have a smooth maximum or minimum, we cannot tell yet, at this location. So we need to find this point, you know, where this what this distance is, and I call it x, where m is maximum. Okay. All right. So let's start drawing the diagram, and as it proves necessary, we're going to take care of this. So kilonewton times meter, kilonewton meter, the units for m, and I draw the x-axis. Let me move it down for m. Things may happen both above and below, or will happen. Okay. So on the moment diagram, I'm going to see things happening at the 4. So moment begins at 0 and goes with a negative slope. Right, so this is a linear moment. I have a constant v, linear moment. So I go linear, slope of negative 15 to a new value from 0 again goes to point B. And what is the moment at B? Again, a negative value. So it's going to be 15 times 2.5. 2.5, that's negative 37.5 kilonewton meters, right before point B. We're at point B. And then I entered or I continue under the distributed load. So moment switches to a parabola. And I have, you know, it starts with a positive slope. It goes to 0 and ends with a negative slope that is less. And well, I can evaluate what the moment at D is. I need to also know where to reverse the parabola, okay, where it reaches its maximum. So let's see what the moment at point D is. I have this value, 37.5, and to it, I'm going to add, well, can I calculate this? So I have a triangle. Yeah, I need to find x, m max at this point, okay? Because I need to know what this positive area is, what this negative area is to find m. The other option is to evaluate this area. I could do that too, going from right to left, and take it as a positive because I'm going right to left. So yeah, we can do that and then verify after finding what x max is. Do you understand what I'm saying? So we go from right to left. Area of the trapezoid is going to give us the moment with a flip sign, a moment at D. And the moment goes to 0 because I don't have any concentrated moments. So 157.1 times 2, that's 314.2. So it goes like here. So this would be the 314.2. And as for the slope, it starts with a negative slope that is big and goes to a zero slope. It cannot go this way because it goes from a whatever positive slope to an even bigger slope, so it has to be this other way, this branch or the last section of the moment diagram. Does it make sense? So working from right to left, I was able to add this piece to the moment diagram. I'm overdrawing. And I know this magnitude here. And it might be too high up. Maybe the moment goes further up. So let's make provision for things that will happen in this here. All right, so let's find where the V diagram goes to zero, because there's where moment goes to zero. So the way of we can do it is to write similar triangles. I can call this A, I can call this B, or you can linear relationship. So you're using similar triangle. I'll say A over B. That is, this piece over this piece equals 162.9. A goes with 162.9 over this other piece, which is not negative, magnitude 37.1. And then I have A plus B, the second equation, because there are two unknowns. So A plus B equals 4. Okay. All right, so one convenient way of doing it is to explicit A from this equation. So I have A equals 4 negative B. So 4 negative B over B equals 162.9 over, actually I take the zero, the decimal point, 71 is fully correct. So further saying it's 4 over B minus 1 equals 162.9 over 371. And I can solve for B. So B is going to be this business plus 1. Okay. Divide by 4 and flip. All right. So 162.9 over 371 plus 1. And then I said, so B over 4. So I divide by 4. I get 1 over B. And if I take a negative 1, I get B. One way of putting it. You can do it your way, and we can verify numbers again. Okay, so 1629 over 371 equals plus 1 equals over 4 equals, and take 1 inverse. So it's 0.742 meters. And that was B. So this is 0.742 meters. This is a little bigger. I mean, it will be bigger. So say negative plus, it was 4 equals, I have 3.258. 3.258 meters. Is it clear what we did? You follow? Don't rely on watching the recording later, because as you turn YouTube on, there are all zillion of temptations. Google is careful to, his monitor, your preferences will start to entice you with, History Channel excerpts or something else. Okay, so let's see what the moment is where it's maximum. So I have negative 37.5, to which I'm adding the area of this triangle. So I go back to what I had earlier, 37.5 negative, plus the area of the triangle, and it will be 162.9 times 3.258 over 2 equals, this goes to 227.9. 227.9, the value. And now let's look at the, So how the parabola will look like. So yeah, it's a positive value. So it starts with a, let's see, this will be, yeah, it starts with a positive slope, 162.9. It goes to a zero slope. So it goes like this. Okay, and then it continues, and I'll be 127. Are we? Is this correct? So I cannot close this diagram with this value. And it comes from above. There has to be a bigger value, or this one has to be a smaller value. Let's reevaluate this. So I said it will be this guy plus this guy times 2. So let me try again. 57.1 plus 157 times 2 over 2. Okay, so it was a mistake. This was not correctly calculated. The area of a trapezoid is going to be this piece plus this piece equals, and then times this value over 2. So I don't know what I did. This is the correct value here should be 214.2. 214.2. And I need to move this a little bit up to where, so it continues like this and then goes like this. There's a it's not a smooth inflection, if it makes sense. So it changes. There's a like the tangent value differs. Okay, and do you remember what I said? The axial maxima is going to be here. Was it 200 and what? So okay, I can do it again. 37.5, which is this piece times the triangle plus 162.9, 162.9 times 3.25.258 over 2 equals plus 37.5 negative equals. Was it 227.9? 227.9 is a maximum. Okay. So if I take this value and if I add to it a negative area, which is, so I said negative 0.742 times 37.1 over 2 equals, yes. So the diagram closes. Again, 227.9 negative the area of the triangle, so will be 37.1 times 0.742 over 2. It's also 214.1. Okay, so it's either this one, but also is, should have written down, so it's 571, the area of the trapezoid, 57.1 plus 157.1 times 2 over 2. Okay, this is going with the trapezoid. Is it clear? All right. So it takes a little bit of an exercise looking at slopes. You know, so it starts like here. I start with a positive slope that goes to 0, which is this point, and then I continue smoothly. Again, I'm on a parabola because of linear shear, and because of this drop caused by the 20K force, I have to change. It's not like a smooth. It doesn't go like this. It's not smooth. There's an inflection point here. So the slope to the left is negative 37.1, and the slope to the right is 57.1. So it's a drop in, it's like you bend, you break an arched piece of wood or something. Anyway, so negative moment, positive moment, and we have the N max. This is what we care about, N max. This is 227.9 kilonewton meters. So maximum moment here. And then I also need to, so it was a maximum bending moment, or rather shear, I apologize. So maximum shear happens at D. So V max, this is going to be 157.1 kilonewtons. So these are the two values that I'll be working with. I need to use moment, the maximum moment, to select an I-beam, as it says here, so IP I shape, and then verify for that what the design factor is. Okay, so let me delimit some space here where we're going to apply the flexure formula. So sigma D is going to be M max over S will be Sx from the table. There's a second problem of this type we're doing. And this is going to be equal to, we're looking here, so static loading, structural steel, so 0.66 SY. Okay, so what is SY? We need to, okay, it's the same, Josh, it's the same structural steel, but a European shape. So this was 50K, well, we need the megapascal, so don't worry. Yes, student. I'm sorry? Oh, because on my diagram this appears bigger. I don't know. It's Monday after a weekend. Yeah, you're right. This is a bigger value. I was also trying to pull the problem to where it shows that I have negative or rather negligible moment, but I have a large shear. Actually, here moment is also rather small. So yeah, you're very right. The bigger value for V is 162.9, 2.9. Thank you for paying attention. All right, so I was heading to the appendix, and we need to find what properties of structural steel and what was it? A992 high strength low alloy available in W shapes only. This is really so A992. Okay, well. And then we look at the yield strength in megapascals. It's 347. So SY megapascals, again, a high strength low alloy steel. And with this, we can continue this calculations to find what required SY. So, or rather SX, minimum required. A value that, as I said earlier, seldomly is available. You need to find one that is at most, or rather at least this. So it's going to be, what is M max? We said 227.9, 227.9. So 227.9 over 0.66 times 347. And this is megapascals. I need to make sure that my moment is in Newton millimeters. So kilonewton meter is also Newton millimeter. Is that right? So I take the 1,000 from the kilonewton and move it to make the meter millimeters. So kilonewton meter is also Newton millimeters. So let's see, and this would be millimeters at power 3. Only this much? Oh, it's pretty small. Millimeters usually. So we said megapascals. It cannot be this tiny. Let's verify. 227 kilonewton meters. Oh, no. I'm sorry. I'm doing a mistake here. So kilonewton. So I have the arm of the moment. This is 1 meter. It's, what was it? 227.9. So what prompted me to stop and think again was this was 0.9 millimeter power 3. So that's nothing. Okay, that's the area of what when I do this. So I'm looking at the force, and this is kilonewtons, and I have a meter. So it's going to be 1,000 millimeters. Okay, and I want newtons. So this will be times 10 to the power 3 newtons. And at an arm of 1,000 millimeters, it makes this 1,000 more. So it'll be times 10 to what? Power 6. Okay. So let's start again. 227.9, 227.9 exponent 6 over 0.66 over 347. 347 equals 95109. I could even neglect this. Okay, so this is a more plausible answer. Okay. A lot of millimeter power 3, but it's closer to, a reasonable value. So what do we need to do? We need to go to the appendix. I can lower the screen to the appendix where let's see, eye shapes, and I need to rotate the view. So this is W, and then next I think it's in metric. No. Eye shapes. Properties of eye shapes. All right, so I think it's where the IP shapes are. And I'm looking at something that is at least, so what do we have? We have like, will be 1 million. 1 and how many zeros? I have 1, 2, yeah, like 1 million. 3 and 3 millimeter at power 3 cube. Is that right? So something, I'm looking at something that's at least 1 million. So we're looking at Sx value. Again, I wrote Fleischer formula using the section modulus rather than MC over I, because now I'm looking for a cross section. So if you combine Ix and C in a single number, it's easier, of course, to, what other way? Okay, so we want something that's at least 1 million. So it looks like this one is a candidate. Everybody agrees? So 1.008 times 10 to the power 6 millimeter. Oh, and this is IY. I'm sorry. So I need to look at SX, I said. So SX. And I have, this is a bit small. This one is the candidate. I'm sorry. So 1.161 times 10 to the power 6 and it's entry N. So how do you specify it? Yeah, IPE depth for 40 millimeters. So use for 0 depth. I'm going to need more values from this table for the second part of the problem, because we need to utilize web thickness, and depth D is part of the, it's this one. So I'm going to take a screenshot and crop just entry N. So Alt print screen, and I go to paint, and I say paste, and I'm going to set, what was it, entry N? Entry N, yes. Was it N or M? Okay, yeah, this one was. So moving this to the top, and then take this guy, copy, and then go back and paste. And I think we can, all right, we can go back to the board. Okay, for structural steel, we don't need that note. And then what? I want to make more room for my, come on, rectangle tool. And can we see it? Yes, we can. All right, so we have, we found the section from consideration of limiting the bending stress according to that recommendation in bending design stress at most, or I said at most, at least, if it goes over, that is 0.66. What will that be as a design factor? If I take one, so 0.66, I take the inverse, it will be a design factor of 1.52. All right, now I'm moving to shear. So tau D, design stress in shear, is going to be, and this is shear caused by bending, so I need to go to shear stress in beams. Actually, it's closer to, I think it's close, is it? To go in reverse? And we have for thin web shape, that is thin I-beams, this equation, 817, okay? I don't know if you can see, you can't. So Alt print screen, and I go paste, select transparent, and move it slightly up. So the equation that we're going to use is this approximate equation 817. It gives us the maximum shear stress caused by the shear force when we have an I-beam. So I'm going to copy that equation. Again, it's an approximate equation, and it goes V divided by thickness divided by H, H being the depth of the, so H is also D, labeled D. Okay, so let me get rid of this. And we're looking at web thickness and the depth 400. So V, the maximum shear, 162.9 over thickness 8.8, and D 400. All right. And this has to be limited. This has to be at most, or at a, yeah, so this has to be less than 0.4 times yield strength in tension. So let's evaluate this. X1, 162.9 over 8.8 over 400. Okay, so I have 0.62 0.46 megapascals. This is a tiny stress, as you can see, and this is less than, so I say 0.4 multiplied by 347. So 0.4 times 347 equals, that's 138.8. So way smaller than the maximum shear stress that is permissible according to code for building-like structure statically loaded. Was it clear? Questions, comments, suggestions for improvement? Remain online for a chance to win a plasma TV. Yeah, so I guess this was the second problem. Again, if you came late, watch the first or the recording. We solved another one with the problem with distributed load. I repeat myself and what? If you learn something at the final exam, you learn it, right? So maybe you learn, it wasn't the perfect final, but you learned something by what? By trying the problem at home out of frustration or something. So for test number 2, I don't think was no fully correct bending moment diagram produced. Load diagram and shear diagrams look fine. For the problem was a distributed load, but not a bending moment diagram. You wanted to, you're still taking notes or take photographs or prepare for asking questions. Okay. So I haven't emphasized it, but it appears lucrative. And I need to lower the screen. Before the only way you can lower the screen is from the podium. So yeah, I overlooked this because I'm not using it and because you don't have it in the Design Machine Element book I'm using next semester. But was that combo, all possible combinations. So yeah, this is a good diagram after all. Okay, so your exam problem, it's something like this up to here, yes? And then you had a section that looked like this. So if the shear is a continuous line without any changes in sudden changes, then the moment is going to be a smooth one, right? So slope goes from positive to 0 and switches to negative in a smooth way. Okay. Here I'm seeing it's an inflection. If this slope equals, hold on, is this correct? I mean, yeah, it is. So we have left and right of this point, same slope, but then it switched from going to still negative, and then goes to 0. Yes. I don't know if you want. This is not quite my diagram. I have other method or to reconcile slope with the appearance of the moment diagram. And as we study deflection is the next chapter, you will see they correlate nicely. So you have distributed load gives you information of slope on the shear diagram. You have shear diagram that tells you the moment diagram because derivative of moment gets you shear, and then this deflection goes as through integration deflection of the derivative of deflection gives you bending moment, derivative of, I meant to say slope gives you moment, and deflection gets you, the derivative of deflection gets you slope. I have yet another problem I want to solve. It's 1:41, so let's go over it. I started pretty late. We're hoping that student will show up. I think what's 12:12. So let's pull ourselves together and do this last problem. It's of a different type. So go to. Actually, I think I can copy it. Copy image, paste, okay. And I need to raise the screen, and I need to raise the board, and you can, while I'm doing it, you can read the text of the problem. So this is about shear flow, sizing the fasteners in an I-beam that is reinforced with some plates, and we use rivets, and we are given the allowable shear force for a rivet, and we want to know at what spacings they should be. There are two. Okay, so essentially we'll take what? We either double this or divide by 2 or multiply by 2 the distance. We could do that. So is it clear what this problem is about? It's the last type of problems from this chapter on shear stress caused by bending. And maybe I should go to the actual chapter. So towards the end of the chapter, we're introduced with another concept with fabricated sections. Okay, composite beams, shear flow. All right, so shear flow is going to be, so it says Q called shear flow. It's found by multiplying the shear stress at the section with the thickness of that section. We know how to evaluate the shear stress caused by bending with this equation, shear force from the shear diagram, first moment of area moment of inertia, and thickness. And then, so we can relate Q to what is left of the early equation. And then distance, so distance between maximum distance, S max, as distance between fasteners is going to be shear, we write this down, F, maximum allowed shear stress per fastener, or the shear force, I'm sorry, per fastener, divided by shear flow, Q. Does that make sense? So if you have a 2x4 that you make it in a in an I-beam, I'm drawing in here, but I can draw with so if I fabricate an I-beam using 3 2x4s, okay, so this is the fastener, and I have FDS. This is the maximum shear force that one fastener can hold. And again, Q is V times first moment of area over moment of inertia. Okay, I can calculate at what distance I need to apply nails to fabricate that I-beam using 2x4s, or I can do a T. Okay. With an I-beam, like our problem with the rivets, it's easier because centroid is it's easily readily available, and total area moment of inertia, it's likewise easy to, don't need the full table to calculate. Okay, but yeah, this is what we need. So for our problem, we're giving this, we can calculate a shear flow, and then that is the shear force per rivet. Don't forget we have two of them, like what? Not that you do it when you fabricate I-beams or T's of 2x4s. So we have two rivets per row, and that's it. Okay, so the area of shear is going to be this one. Okay, and we need to do what? Find information about this I-beam. Firstly, we recognize that the centroid of the reinforced I-beam is the same as the original I-beam. Okay, so let's find centroidal moment of inertia for the IPE I400. Okay, so we have I total, which is I from this equation, okay, is going to be I of the I-beam plus, and again, I know where the centroid is. The centroid will be half distance. So it will be 2 times I of the flat, and then plus, and I have 2 of them, the parallaxis theorem term. So it will be 2 because of 1 and 2. And then I have the area of the flat times the distance square. What distance? Between the centroid of the flat and the centroid of the assembly. Now we know the centroid of the assembly, it's in halfway between the, coincides with the centroid of the original I-beam. So this makes for an easier problem to solve. With just one plate on top, then we need to go through, the full table. Does it make sense? Okay. So this is the I-beam, and this is the flat. And because we have 2, I multiply by 2 in 2 places. So let's find this first. We need to go to the appendix. And so again, I have 40. I left my my book so at home actually. So I'll need to ask for your participation. So it says practice the I shapes, and this is we've been there. It was a metric. No, the next one. This one, and was the 400. Was it the one that we chose for? And I think we chose this one. We've been here before, have we? Okay, so maybe they had a bias for this this cross section. So what are actually I'm going to just take a alt print screen and add it to this problem. So select all and paste, and I grab this. Copy, paste. Okay, so what does it go here is going to be the IX value. It says power 8. I think it does. So 2.321 times 10 to power 8 millimeters. I said 8. And then I have the flats. 2 times, and the flat is 12 by 180. So either back to or rely on memory. is this one, right? So we need Ix, it's BH at power 3 over 12. So this guy is going to be 180 times height 12 at power 3 over 12, and then plus 2, because I have 2 plates, and then the area of a flat is going to be 180 times 12, and then times the distance squared. So this is the distance that we need to, and it's the same. Again, analysis for this pair, this set of rivets is the same for the set one because of symmetry.